Science rules! Meet a science hero, Leonhard Bernoulli. Have you ever wondered how a gigantic metal bird, an airplane, can soar through the sky? Or how a soccer player can make a ball curve like magic? It's not magic, it's science! And a lot of it has to do with a brilliant scientist from a long, long time ago. His name was Leonhard Euler, who was a close friend and collaborator of the Bernoulli family, particularly Daniel Bernoulli, the one we credit with this amazing idea. Daniel Bernoulli was part of a whole family of super smart mathematicians and scientists. Think of them as the rock stars of science back in the 1700s. They were always asking questions, observing the world, and trying to figure out how things work. It's what scientists do. Daniel Bernoulli was super interested in fluids. Now, when you hear the word fluid, you might just think of water. But in science, a fluid is anything that can flow. That includes liquids like water and juice, but it also includes gases, like the very air we breathe. Bernoulli spent a lot of time studying how these fluids move. He wanted to understand the rules that govern their flow. All right, let's get to the heart of the matter. What is this big idea, Bernoulli's principle? It sounds complicated, but I promise it's not. Here it is in a nutshell. Where a fluid is moving fast, its pressure is low. And where a fluid is moving slow, its pressure is high. That's it. Fast-moving fluid means low pressure. Slow-moving fluid means high pressure. They are inversely related, which is a fancy way of saying they are opposites. When one goes up, the other goes down. Think of them as being on a seesaw. When speed goes high, pressure goes low. Simple, right? Imagine you and your friends are walking down a wide, empty hallway at school. You can all walk slowly, side by side with plenty of space. There's no rush, no pushing. This is like a slow-moving fluid with high pressure. Everything is calm and spread out. Now, imagine that wide hallway suddenly narrows into a single small doorway. To get everyone through the same doorway in the same amount of time, you all have to speed up and squeeze together. You're moving much faster now. This is like a fast-moving fluid. Because you're all zipping through a tight space, there's less pushing outwards on the walls of the doorway. That's the low pressure. Let's try another one. Think about a river. When the river is wide and deep, the water flows slowly and majestically. So how does this speed and pressure thing get a massive, heavy airplane off the ground? It's all about the special shape of the airplane's wings. An airplane wing isn't just a flat board. If you look at one from the side, you'll see it has a specific shape called an airfoil. The top surface is curved and a bit longer. The bottom surface is flatter and shorter. This shape is the secret ingredient. It's designed to manipulate the air and create an upward force, lift. As an airplane speeds down the runway, air rushes towards the wing. When the air hits the front edge, it splits into two streams. One stream goes over the curved top. The other stream flows along the flat bottom. The top surface is longer, so that air must travel farther to meet the bottom stream at the trailing edge. To cover more distance in the same time, the top air moves faster, like two runners on a track. The outer, longer lane must run faster to finish together. Bernoulli time. Faster moving air means lower pressure. The air zooming over the top creates low pressure above the wing. The slower air underneath keeps higher pressure below the wing. Pressure difference equal, sign a net upward push. Nature balances by moving from high to low pressure. This upward push is lift. When lift exceeds the plane's weight, it leaves the ground and flies. Faster plane speed, faster air over wings, stronger lift. Let's zoom in on that airplane wing again, because it's just so cool. The shape of the airfoil is engineered with incredible precision. Pilots can even change the shape of the wing slightly during flight using flaps and slats. When a plane is taking off or landing, it's moving slower, so it needs more lift. By extending flaps from the back of the wing and slats from the front, the pilot makes the wing's top surface even more curved and longer. This forces the air to travel even faster over the top, creating an even bigger pressure difference and generating more lift at slower speeds. It's like giving the wing a temporary superpower. Think about a bird. A bird doesn't have engines, but it can fly beautifully. How? It uses the same principle. A bird's wing has that same airfoil shape, curved on top and flatter on the bottom. By flapping its wings, the bird creates its own airflow. A helicopter's rotor blades are essentially spinning wings. Each blade is shaped like an airfoil. Even a simple paper airplane relies on this. When you throw it, the air moves faster over the top of those curved wings. You are being an aeronautical engineer, using Bernoulli's principle to make paper fly. Let's move from the sky to the sports field. Have you ever seen a soccer player take a free kick and make the ball curve around a wall of defenders and into the goal? It looks like they're breaking the laws of physics, but they're actually using them. This amazing trick is another fantastic demonstration of Bernoulli's principle at work. It's all about putting a spin on the ball. When a player kicks the ball, they don't just kick it straight on. They strike it off center with the side of their foot, making the ball rotate rapidly as it flies through the air. As the spinning ball soars forward, it drags a thin layer of air along with it because of friction. Let's imagine the ball is spinning clockwise as it moves from left to right. On the right side of the ball, the surface of the ball is spinning in the same direction as the oncoming air. The air and the ball's surface are moving together, so the air flows past smoothly and quickly. It's like swimming with the current. Everything is fast and easy. The air on this side is sped up by the spin. Now, let's look at the other side, the left side of the ball. Here, the surface of the ball is spinning against the direction of the oncoming air. This creates more friction and turbulence. It's like trying to swim against the current. It's much harder, and the flow is disrupted and slowed down. We have fast-moving air on one side and slow-moving air on the other side. And what does Bernoulli's principle tell us? This pressure difference creates a net force on the ball. This force is what makes the ball swerve or curve in midair. This curving effect, caused by a spinning object moving through a fluid, has a special name, the Magnus effect, and it's just a specific application of Bernoulli's principle. You see it all over the world of sports. A baseball pitcher can throw a curveball slider fastball that seems to rise by putting different spins on the ball. Each type of spin creates a unique pressure difference around the ball, causing it to swerve left, swerve right, swerve down, or even slightly up, fooling the batter. The pitcher is a master of applied fluid dynamics, whether they know it or not. The same principle applies in tennis. When a player hits a powerful shot with topspin, the ball is spinning forward as it flies. This creates high pressure on top of the ball and low pressure underneath. This pressure difference creates a downward force, causing the ball to dip sharply and land in the court. In the 1920s, a German engineer named Anton Flettner built a ship that used the Magnus effect for propulsion instead of sails. Even in golf, the Magnus effect is crucial. This generates lift. Okay, let's bring this principle right into your home. Have you ever been taking a nice warm shower, and suddenly the shower curtain starts to move inward, sticking to your leg? It's kind of annoying, right? You might think a draft is blowing it in, but the real culprit is, you guessed it, Daniel Bernoulli. This is a perfect everyday example of his principle in action. It's a little science experiment that happens every time you turn on the water. Here's what's happening. When you turn on the shower, you have a stream of fast-moving water air inside the shower stall. The water droplets drag the air inside the shower along with them, creating a current of moving air. According to Bernoulli's principle, what happens when you have fast-moving air? You get low pressure. So inside the shower, right next to the curtain, the air pressure drops. It becomes lower than the air pressure outside the shower stall. Meanwhile, the air in the main part of your bathroom, outside the shower, is relatively still. It's not being dragged along by a powerful spray of water. So this still, calm, slow-moving air has a higher pressure. Now you have the classic setup. Low pressure inside the shower, high pressure outside the shower. The universe likes to be in balance, so the higher pressure air outside the curtain tries to move into the lower pressure area inside. Since the shower curtain is a lightweight, flexible barrier between these two pressure zones, it gets pushed. So the next time it happens, you don't have to get annoyed. So, what's the big takeaway from all of this? Bernoulli's principle, the simple idea that fast-moving fluids have low pressure and slow-moving fluids have high pressure. It's one of the most important concepts in all of physics. It might seem like a small detail, but it explains feats of engineering and it explains feats of nature. It demystifies the magic of flight and the curve of a soccer ball, showing us that the world operates on a set of understandable rules. And understanding those rules is what science is all about. It's about being curious and finding the answers. This principle empowers us. By understanding how pressure and speed of fluids are related, Engineers can design incredible machines. They can shape a wing to lift a 400-ton jetliner, design a spinning rotor to make a helicopter hover, or build a pump that can spray a fine mist. Knowledge of this principle allows us to harness the invisible forces of the air and water around us, turning them into tools that have completely changed human civilization. Understanding a concept like Bernoulli's principle changes the way you see the world. The next time you see a bird gliding on the wind, when you watch a baseball game, when your shower curtain attacks you, you'll know exactly why. Science is cool,